great to be back. I always tell my students about one screw up, and my screw up has been to leave this place. New Haven is not the same as Salt Lake City. So, anyway, today I'm going to talk about what I've been up to in the last few years, and one of the things I've been doing is trying to learn a little bit, to try to understand how structure builds up purely in the dark sector, meaning I'm going to talk entirely about dark matter. And that's what I do with the dark sector. And in particular, I'm going to present an analytical model for the assembly of dark matter halos. Okay? And I should point out that this is work that's largely done by my graduate student who's just finishing up this year, Arthur. His real name is Fangju Zhang, but thankfully he goes by Arthur, and who has done a lot of the work I'm going to present you. Now, since this is an audience largely consisting of physicists and students, I decided I'll start with a 10-minute crash course, Galaxy Formation 101, sort of to paint a big picture of how we envision galaxy formation in this sort of lambda CDM paradigm. And then move on to talk about halo assembly histories. I'll talk about how halos build up their mass over time. I'll show how that links in understanding how they get substructure and how that substructure evolves over time. And then once we have the analytical model set in place, I'm going to apply it to something that's called the too big to fail problem. This is a famous problem that was pointed out about 4 or 5 years ago, 6 years ago now, but maybe the CDM paradigm may be in trouble, and I'm going to argue that that's not the case. Okay. So let's start with galaxy formation, the standard paradigm. And like every good story, this one starts with once upon a time. So once upon a time, something happened. Okay? Space-time was created, the hot Big Bang event. And exactly how that happened and what was going on, we don't really know, but it doesn't really matter because we have postulated that very, very shortly after the Big Bang, and when I say very shortly, I mean like 10 to the minus 34 seconds after the Big Bang, something happened. Namely, the energy density of the universe became dominated by that of a scalar field. The scalar field is called the inflaton. Now, all you need to know is that when the energy density is dominated by a scalar field, then that causes the universe to undergo exponential accelerated expansion. Okay, so the universe goes through this phase of really, really rapid expansion. Now, this lasted only about 10 to the minus 31 seconds. Okay, that's like nothing, right? 10 to the minus 31 seconds. But during these 10 to the minus 31 seconds, the universe expanded by, 21 orders of magnitude. And it basically means that in that 10 to the minus 31 second time frame, something that has the width of a human hair expanded to something as large as the Milky Way galaxy today. That is a dramatic expansion. So that solves a bunch of problems. It explains why the universe is flat, because any curvature that there was in space-time before that time just got stretched out enormously, and the universe basically is flat. Okay? Not only that, the scalar field, this inflaton scalar field, is a quantum field. And like any quantum field, it has quantum fluctuations. And these are quantum fluctuations in the energy density at any given point in space. And now imagine you have one of these energy density fluctuations. At some point, the energy density fluctuates a little bit up, and yank, you stretch it out to enormous sizes. These energy density fluctuations manifest themselves later on as fluctuations in the metric of space-time. So these quantum fluctuations in the inflaton, 10 to the minus 31 seconds after the Big Bang, give rise to perturbations in the space-time metric on all scales. In fact, it are these quantum fluctuations in this scalar field that are the seeds of all of structure formation. And in this picture, therefore, a galaxy like our own ultimately has its origin in a fluctuation in a quantum field 10 to the minus 31 seconds after the Big Bang. It's a pretty crazy story. These quantum fluctuations, they grow. They grow, and we can see them 380,000 years after the Big Bang in fluctuations in the temperature of the cosmic microwave background. 380,000 years after the Big Bang, the photons decouple from the baryons, the electrons and protons combine together to make neutral hydrogen, and the electrons stream off. These electrons give the cosmic microwave background, and what we see are tiny fluctuations in the temperature of this radiative fluid. Okay? And we have probed these these temperature fluctuations, and the temperature fluctuations directly map into these density fluctuations that have their origin in these quantum fluctuations. And there's a wealth of information in these temperature fluctuations. And that wealth of information people have melted out. And from that, we now know that the universe consists only for about 4% out of the regular matter, electrons, protons, neutrons, aka atoms or baryonic matter, or whatever you call it. Then there's about 23% dark matter, probably cold dark matter. That cold just means it's a certain property, and for all practical purposes, you have to think of dark matter as a collisionless fluid. It only feels gravitational force. It may have a weak interacting force, but that's not really important. It feels gravity, and other than that, it's a collisionless particle. And then the other remaining 73% is something even more mysterious in the dark matter. It's dark energy. Okay? So more than 96% of the universe is made up of stuff that we don't know what it is. Okay? We've never seen it. We have ideas what it might be, but your idea is as good as anyone. These fluctuations that we see 380,000 years after the Big Bang, they grow. And they grow by something called gravitational instability. And basically, it's just gravity at work in those days. Okay? And what happens is, you have a fluctuation, say you have an overdensity. That overdensity, of course, exerts a little bit of force on its neighboring, and that pulls matter in towards itself. And therefore, that overdensity becomes a larger overdensity. And it does that by pulling matter out of the underdense region. So this is like the pure capitalistic principle where the rich get richer and the poor get poorer. Here, the overdense regions get more overdense, and the underdense regions get more underdense. And that's just gravity. Okay? And as long as these fluctuations are small, we can work this out analytically. We call this a linear regime, and we can work out analytically how they grow. Now let's focus on one of these perturbations. Suppose we have a spherical region that's an overdensity, okay? And ask what's going to happen. This overdensity is expanding with the universe. The universe is expanding, and as overdensity sits there, it expands with the universe. It gets larger in size. But at the same time, some matter is flowing towards it, and therefore its overdensity grows. So its density goes down because it's expanding, but its overdensity with respect to its neighborhood goes up. And once that overdensity becomes of order unity, okay, then this perturbation at some point says, you know what the heck with this universe, I am so massive, I'm so overdense, I'm going to collapse under my own gravity. Okay? So this thing is expanding, and at some point it becomes so overdense, it says, you know what, I'm turning around, I'm going to collapse. And that's what's happening. It's going to collapse. So now imagine one of these shells of dark matter. Imagine, a theorist, imagine a shell, spherical shell of dark matter. It's expanding, turns around and starts to collapse. It collapses, collapses, it collapses, and collapses basically to the point where it's in a point. And then it moves through itself because it's collisionless, and it comes out on the other side. So the shell collapses and goes out to the other side. It turns its kinetic energy back into potential energy, turns around, and goes back. And if there was only that shell in the universe, it would just do that. It will go back and forth, oscillating, turning kinetic into potential energy, and back and forth. That's what a shell of dark matter would do. It would just move through itself. Now, unfortunately, there's not just one shell. There are smaller shells and bigger shells that belong to that perturbation, and they're all going around, and they move through each other, and it becomes a big chaotic mess. Of all these shells wobbling through each other, they cross each other, and it becomes highly nonlinear. We can't write down what's going to happen. But we're going to run numerical simulations of this collapse process, and what we see is that this process ultimately, through a process we call virialization, gives rise to a dark matter halo in equilibrium. And the simulations have taught us that these dark matter halos all have a universal density profile. It's known as an NFW profile, for Navarro, Frank, and White. So, for some reasons that we still do not understand fully, this virialization process gives rise to virialized dark matter halos with a universal density profile. Now let's look at the baryons, because these perturbations are not just purely dark matter, they are dark matter plus baryons. So what's going to happen to these baryons? Now imagine this shell being made out of baryonic matter. It's doing the same thing. It's expanding. It's going to turn around. It's going to collapse. It's going to collapse. Going to collapse. Collapse until it comes to the point. And now it deviates from the dark matter because it cannot move through itself. It feels electromagnetic forces. And what's going to happen is it shocks. It hits itself. It shocks. And when it shocks, it converts all that kinetic energy that is falling into heat, into internal energy. So this gas heats up. And basically this process in the end then gives me a relaxed, very large dark matter halo with a hot bath of baryons in them that are roughly in thermal equilibrium with the potential well in which they're moving. Now these baryons can do a trick, what the dark matter cannot do, and that is radiate. These These dark baryons, it's heated up to high enough temperature that's basically all ionized. So you have electrons moving around and protons, and whenever an electron sees a proton, it feels a Coulomb interaction, it gets accelerated, and when you accelerate a charge, it radiates. So this hot photon fluid, this hot bath of baryons is radiating away binding energy in terms of photons. And when you radiate away these binding energies, the baryons are going to contract. And they contract. They're going to contract. Okay? They radiate away the binding energy. Now, these baryons, and also dark matter, also have a little bit of angular momentum. It comes from the fact that there are more than one perturbation in the universe, and when this perturbation is growing, there are neighboring perturbations that are also growing, and they exert torques on each other. And these torques slowly spin up these dark matter perturbations and the baryonic perturbations, and by the time you have this halo that's relaxed and virilized, the halo is left with a little bit of angular momentum. And the baryons have basically the same amount of angular momentum, specific angular momentum. And now you radiate away these photons, and these photons are radiated isotropically in random directions, so they carry away binding energy, but there's no net loss of angular momentum, because it's an isotropic process. So the angular momentum basically is conserved. And what happens if you take a gas cloud, and you let it condense and conserve angular momentum? It's going to spin up. Okay? Just like an ice skater spins up when he or she pulls in her arms. So this gas condenses, spins up, and basically forms a disk in which the gravitational force is balanced by the centrifugal force of the gas moving around. This disk has a very high density, and it's cold. That means it's ideal for star formation, and voila, a galaxy is born. Okay? So that's basically how we think that a galaxy forms out of this collapsing halo. The one thing that I didn't mention yet is that there are neighboring halos that also collapse. And these neighboring halos then feel the gravitational force of the bigger halos around them, and they fall towards the bigger halos. And when they fall into a bigger halo, they give rise to substructure in that bigger halo. They survive, they fall in, and they now start to orbit around in that bigger halo, and that's how you basically give rise to halos that have a lot of substructure. And each of these little halos may have in the meantime formed a little galaxy in them, and that's how you can make a cluster of galaxies. Okay? So far I only give you an idea about how you can form these disk galaxies out of angular momentum conservation and cooling. So how do we make these other kind of galaxies, these ellipticals? Well, the answer is very simple. And as we already told you, that these dark matter halos merge all the time. They merge together. Okay? That's just due to gravity. And when the halos merge, the galaxies in them can also merge. And when you take two disk galaxies and merge them together, you're going to make an elliptical. And it's very easy to understand, because a disk galaxy basically is a low entropy system. All the gas is doing the same thing, going around in a nice, ordered, circular motion. Okay? Nature doesn't like low entropy. Okay? So when you kick a disk, when you disturb it, it will try to crumble up into something more higher entropy. And what's more higher entropy than a blob of things in which the particles go randomly around, aka an elliptical galaxy. So you merge two disks, and you make an elliptical, and therefore you expect to find more ellipticals in a region where there's been a lot of merging, like in a cluster environment, okay? And that makes some sense. Okay? So this is basically our current picture of galaxy formation. In a lambda CDM universe, the lambda didn't appear in this story, basically doesn't do much. But the CDM, the dark matter, really sets the stage for all this action. So if you want to understand galaxy formation, you first have to understand how this dark matter builds up over time. Okay? Any questions about this? If not, then we can move on to halo assembly histories. Now, I should start by pointing out that we were trying to build an analytical model. And when we submitted our first two papers in the series, we got a referee report back that says, well, in this day and age of numerical simulations, would you want to construct an analytical model? Clearly, an extremely short-sighted reply from a referee who clearly is not very smart. The good news is, when you get a referee report like that, you immediately know who she is, right? So at least we knew who a referee was. But let me actually take this seriously and try to answer, give you a motivation for why we want to construct an analytical model. First of all, numerical simulations are just that. They're numerical simulations. And if you look up in the Webster Dictionary what it means to simulate, you'll find the following. To give or assume the appearance of, often with the intent to deceive. Okay? I'm not making this up. Look it up. Okay? So that's already worrying. Okay? Then there is the fact that simulations have a limiting mass and force resolution. Okay? For reasons that I will explain later, sometimes you want to simulate, say, 1,000 Milky Way halos. Okay. And you want these Milky Way halos have a mass of about 10 to the 12 solar masses, and you want to resolve them with a resolution so that you can actually resolve sub-halos of 10 to the 8 solar masses that are moving around in this halo. And you can basically work out that that basically means you need to run a simulation with about 150 billion particles. Okay? That's about 1.5 times or 15 times as large as one of the biggest simulations run today, the very famous simulation called the Millennium Simulation. So that's a huge requirement. Okay? That costs a lot of CPU time. Not only that, then you need to waste 20 PhD theses on analyzing the damn simulation. And then someone comes along and says, oops, omega matter and sigma 8 changed, we have the new Planck results. You gotta run your simulation again, because, sorry. Okay, so this is, it takes a lot of time and effort. Okay? The analytical model that I'm going to present you can do the same thing in 20 minutes on this machine. Okay? So it has advantages. Then there's ambiguities with the simulation. It's one thing to run your simulation, but then you need to go in and identify a halo. And you will be surprised to know that 25 years after, or I don't know how many years it is since we ran the first simulations, we are still bitching on about how should we properly define a dark matter halo. You need to run a group find or something, group particles together and say, this is the halo. And everyone does it slightly differently, and there's still no consensus. There's no consensus about where the halo stops and where the center is, and it's amazing. So you can give the same simulation to 10 different people, and 10 different people will give you back 10 different answers about how many halos there are, of what mass, etc., etc. Okay? So the simulations are not set in stone. But above all, the real reason, I think, is the following. Why are we running simulations? Ultimately, you're running simulations because you want to try and understand something. Okay? Ultimately, these simulations are run because they're involving highly nonlinear physics. And what you want to get out of the simulations is something that captures what is going on in simple terms. Okay? And that's exactly what the analytical model that I'm going to present you is trying to do. It's trying to describe in simple terms what we have learned over the years from all the simulation. All right, so if the referee's in the room, I hope you're not satisfied. Well, you're probably pissed off at me now. Okay, so let's start with a merger tree. What is a halo merger tree? This is an anatomy, this is a picture of a halo merger tree. And the way you should read this is as follows. Here's a dark matter halo at redshift, say, 0 today. If you go to an earlier time in the universe, or an earlier output in your numerical simulation, it turns out that the mass that's in this halo is distributed over a bunch of different halos. These are called the progenitor halos. And you can go to one of these progenitors, and at the earlier redshift, it breaks up in progenitors, etc., etc., etc. And this is how we construct what we call a halo merger tree. And basically, this halo merger tree describes how the halo builds up over time its mass. Okay? Now, often what we do is we define something called the main progenitor history. Some people call it the mass assembly history. Some people call it the mass accretion history. Okay, it's all the same thing. But it's the following. You go to this halo, and you go to its previous output, and you identify the most massive progenitor. Then you take that most massive progenitor, and you go back, and of that most massive progenitor, this is the most massive progenitor. So it's the most massive progenitor of the most massive progenitor of the most massive progenitor, etc., etc. That's what we call the mass accretion history. And the idea is that these things accrete onto the main progenitor. What they accrete on, they're always the smaller of the two, and they become now a subhalo. We'll see that later on. Or actually, we're going to see that now, right? Now. Right? So this guy, this system accretes onto him and becomes a subsystem of this one. This one was already a subhalo here, so this is now a subsystem. And what you see is that this hierarchical formation of a dark matter halo at redshift 0 has given rise to a hierarchy of substructure. You have subhalos, which themselves have subhalos, which themselves have subhalos, etc., etc. And ultimately, what our analytical model is trying to do is to sort of describe how many of these things we're going to have in a given halo today. And we're going to do that by using not numerical simulations, but by an analytical method to construct merger trees. And this is very technical. This is called pressure sector theory. I'm not going to bore you with it. But the upshot is that a pressure sector theory, okay, is an idea that basically gives you the progenitor mass functions. Basically tells you, given a halo of mass m today, what is the probability that at a redshift earlier than that, it had a progenitor of mass little m? And once I know the progenitor mass function, I can draw realizations of my merger tree. That's basically the idea behind it. Okay? And how exactly you do that, there are subtle differences in that. It's not set in stone, neither is this. What we did in 2014, we compared a whole bunch of different ways of constructing merger trees from pressure theory. And it turns out that there was one algorithm that really stood out as being the best in terms of reproducing most closely the simulation result. Okay? So we're working on the hypothesis that the simulation is correct. Okay? And that's the Parkinson et al. 2008 method, and that's what we use to construct the merger trees. Okay? We're going to compare our results ultimately to another simulation. This is a very large simulation, the Bosch simulation. Here are the cosmological parameters. Okay, so basically, for the experts in the room, these simulations have been analyzed with a very nice phase-space halo finder that uses all the phase space information of all the particles called Rockstar. And these halo catalogs have been combined to make merger trees for these halos. Okay? And these merger trees and halo catalogs are all publicly available. Here are the websites. Okay? So you can all go and download it. It's all the data. But it's all publicly available. And that's what we're going to compare our model to. So one thing you can do is you can go to these merger trees from the simulation, and you can construct, from these merger trees, you construct the mass accretion histories. Okay? The most massive progenitor, the most massive progenitor. And you do it for each individual halo, and then you pack all halos in a given little mass bin, present day mass bin, and you say, what is the average mass accretion history of a halo of that mass? And that is what is shown here. Okay? So on the top is the mass of the main progenitor at time t divided by the mass at redshift 0 as a function of time. And here I plot the same thing but now in logarithmic units. Okay? This sort of better emphasizes what happens early on. This better emphasizes what happens late on, at later stages. Different colors correspond to different masses of the halo today. A blue line here corresponds to a halo that at redshift 0 has a mass of 10 to the 11 solar masses, about 10% the mass of the Milky Way. And the red curve is basically a very massive cluster, something like the Coma cluster. And the first thing to notice is that more massive halos form later. And that is just hierarchical structure formation. Little things form first and they build up the bigger thing by merging together. Okay? So that's the first thing that you notice. The other thing that you notice is that the lines get a bit wobbly here. And that's because in this simulation box, this is a finite size volume, these massive halos are rare, so in a small fixed volume we only have a handful of massive halos. If I construct an average, the average gets noisy. That's what you see. It's just the limitation of the simulation. You also see here dotted lines, and that's basically because you run out of mass resolution. If you take a low mass halo and you follow it back in time, its main progenitor gets smaller and smaller and smaller, and at some point the simulation simply can't resolve it anymore. So you run out of juice, basically. Right? And that's basically what you see here. Okay? And now we can compare that to what we get out from this analytical method, and it looks like this, and it looks very similar. Okay? So this is sort of a blow-up of this area, so as I said before. But there's two differences. There's no wobbly lines, because I don't have that problem. Okay? And I don't have any problems by going to a very high redshift. Okay? This method just does not suffer from that. And you can put individual colored curves on top of each other, and the agreement is exquisite. Okay? So I would say that this method is as good as the simulation, as accurate as the simulation, and it doesn't have the flaws of the simulation of having a limited volume and a limited mass resolution. Now, for those of you with good eyes, you may have noticed something special, namely that these mass accretion histories look all very similar. In fact, if you look at these things here, it looks like if I just squeeze the x-axis a little bit, I can just put them all on top of each other. And it turns out that's exactly correct. You can do that, and you can find a time coordinate transformation, a coordinate transformation of this axis, for which they all fall right on top of each other. Okay, and that's given here. And the simulation results have the same behavior, except for the problems with the resolution and the wobbly stuff, but they all do the same thing. And what it basically means is that the mass accretion histories are universal. Not only are the density distributions of the halos universal, they also build up their mass in the same way, in a universal way, at least when expressed in terms of a proper time coordinate. Now, the time coordinate is listed here. For those two people in the room, maybe that know projector theory, they will recognize this thing. They will recognize that it's a particular thing in projector theory that appears all the time. Kind of makes sense. This also has all the cosmology dependence in. It turns out that if I do this for different cosmologies, it's always the same thing. The structure is independent of cosmology. As long as I use that time coordinate, I can use this mass accretion history to describe a halo independent of its mass independent of the cosmology that they go. And it basically means there must be something behind this. Why are all these things building up the mass in the same way? What is the principle? Yes?
So by the same thing, what do you mean? Do you mean identically the same?
Identically the same curve.
Curve.
If you go for different cosmology,
Of the time.
and I compute this time coordinate, and I plot this quantity, it looks exactly the same.
So all that's changing is the definition of the time coordinate.
Yes. So that goes into the cosmology here. This is the mass variance, and this is the collapse range.
Wow.
And if you think about it, why is this? It actually has a very simple explanation. We're describing something that's only subjected to gravity. Gravity is the only force that matters here. And gravity is perfectly scale-free. And what are the initial conditions out of which this stuff formed? These initial conditions were these little perturbations, and these little perturbations were imposed by inflation, by yanking out quantum fluctuations, and that basically is scale-free. That's why the initial power spectrum of fluctuations is basically scale-free. So you have scale-free initial conditions acted upon by a scale-free process. It's not that surprising in hindsight that you get something that looks very universal. We'll come back to this in a minute because it gets even better. This is now, another thing you can do is, it turns out that the internal structure of a dark matter halo, for those of you who are familiar with this, will know that more massive halos are less concentrated than low mass halos. So they have the same universal density profile, but the concentration of the profile depends on halo mass. And it turns out, and numerous people have shown it in the past, that that's directly correlated with the mass assembly history of the halo. The reason why the low mass halos are more concentrated is that they assemble earlier. They assemble earlier when the universe is still denser, and that's why they end up being more concentrated. And people have made models for that. And you can make this model. That means that not only can I predict how my halo builds up over mass, I can also use that model to predict what is the structure of that halo. And if I know the structure of the halo, I can calculate the potential well. I can calculate the circular velocity curve of that halo. And what I'm plotting here are predictions from that model for what is the maximum circular velocity curve of my halo as a function of time normalized by its present day value. And you should remember that the central potential of this halo is directly proportional to this Vmax squared. So you can think of it as this is how the central potential builds up over time. Okay, and again, the simulation results are here, and the analytical model is here. The agreement is very good. And what you immediately see, and what I want you to remember, because it's kind of important to remember that when you want to think of galaxy formation, is if you look at this value of Vmax, for these low mass halos, it doesn't do anything in the last basically 8-9 gigayears. These central potentials build up very rapidly. The potential builds up very rapidly. The central potential doesn't change from redshift, 4 or 5 till today. The only thing that happens is mass gets stacked onto the outskirts, but the central halo is no longer affected. The central halo builds up, and then you pile up some mass in the outskirts. Okay? And that's a very useful picture to have in mind for how halos build up over time. So now that we have described the assembly history of the halos, we're going to use it to say something about the dark matter substructure. And first I want to motivate again why am I interested in this substructure. There's a variety of reasons. Okay? One of them is halo occupation modeling. This is what Zheng and I have been working on for a long fraction of our careers, is trying to map how many galaxies are there per halo. Well, if galaxies live in halos, then the number of satellite galaxies in a halo is going to be related to the number of sub-halos in the halo. So if you're interested in understanding how many galaxies there are per halo, you need to know something about how many sub-halos there are per halo. Okay? It's the first, that's sort of the mapping. The other thing that sub-halos can do is they can cause flux ratio anomalies, right? Due to gravitational lensing. When you have gravitational lensing, okay, the light goes through a potential well. These substructures are perturbations of that potential well, and when the light goes through that, it gets slightly perturbed. So that causes perturbations in the light diffraction path. And these perturbations manifest themselves as flux ratio anomalies and time delays. And there are very powerful ways in which people can actually probe how much substructure there is in these potential wells that do this lensing. And again, if you want to touch base, you want to basically have an understanding of how much substructure do we predict. Subhalos can heat stellar disks. As I told you, a disk is a low entropy fragile structure. If you were a disk sitting in the center of a potential and every now and then a big dark matter halo comes zooming by, you as a disk get disturbed and you heat up, you thicken up. Okay? So the fact that we see disks to be very thin already tells you something that apparently this is not a very effective process. So there can't be too many massive substructures in the very center. Okay? So if you want to understand stellar streams, okay? Stellar streams are the fact that satellite galaxies, when they fall in, they get stripped. And the material gets stripped off and produces these beautiful stellar streams. There's a lot of work going on in that direction. Again, it's related to substructure. And for those of you interested in direct detection, or not direct detection, detection of dark matter via annihilation, you have to realize that annihilation comes from the fact that two dark matter particles do something together. And therefore, the annihilation strength of the dark matter goes as a density squared. And if something goes as a density squared, it means it's susceptible to the clumpiness of the material. So if you take a dark matter halo with no substructure, or you take the same amount of dark matter but put a lot of it in substructure, you predict very different annihilation signals. In other words, the substructure gives rise to a boost in annihilation signal. And therefore, if we would ever measure this annihilation signal, okay, and we want to turn it into a measure of what does it mean for the dark matter particle mass, we need to know what the boost factor is. We need to know how much substructure there is. So substructure has a lot of applications. So let's go back to our merger tree. As I said, these things here are giving rise to substructure. Okay, and we're going to distinguish between first order subhalos. These are halos that directly accrete onto the main progenitor. That basically means that those things at redshift 0 are going to be subhalos. We also have second order subhalos. Those are the things that accrete into a first order subhalo and then into the main progenitor, and therefore at redshift 0 they give rise to subhalos. They're going to be a subhalo of a subhalo. And this way I can go to third order, fourth order, etc. Okay? And what I'm going to do is I'm going to define the unevolved subhalo mass function, which is the mass function says how many subhalos does a halo of this mass accrete over its history over a given mass at accretion. Okay? So I go back and I look at this halo and I look like, aha, this is a halo that's accreted and registered this mass. I go back to this guy, this is the mass at accretion. After this halo is accreted, we'll see it's going to lose a lot of mass due to tidal stripping and all of the processes. Okay? But the unevolved subhalo mass function counts the mass of the subhalo at accretion. Okay? So we can do that, and I can write down this unevolved subhalo mass function for halos of first order, second order, third order, first order, and add them all up. You get a subhalo mass function of all orders. Unevolved subhalo mass function. In other words, the way to think about that, these are the masses of the building blocks that I put together to build up my halo. The open circles, not open circles, the gray circles are simulation results. They agree with this analytical model prediction. And here comes the most important thing. This unevolved subhalo mass function, when written as function of the normalized mass, normalized by the present day mass today, is universal. If I change my cosmology, or I change my value of the present day value of the host halo mass, this function looks the same. And this has very deep implications. This basically means that every halo, in a statistical sense, because this is the average, builds up from the same building blocks. The only thing that differs from one halo to the other, or from one cosmology to the other, is the time at which these build up. Low mass halos build up from the building blocks early. Late mass halos build up late. But it's a purely self-similar process. They build up from the same building blocks. And that's a very deep thing to remember, because that allows you to immediately understand all the scalings you're going to see for the subhalos that are coming up. So remember that. So it's the same building blocks. The only thing that differs from one halo or one cosmology to the other is the time at which you build them up.
Question?
Yes?
So is that based on the assumption that you're starting from these quantum fluctuations, and therefore every halo actually has started kind of from the same initial condition, and that the sampling of that initial condition is adequate, that each one actually has a kind of
That's a very good way of thinking about it, yes. It's basically every random patch of the universe, okay, some of which will turn around and collapse into a halo, basically is, inside it looks self-similar. And that's because the fluctuations themselves have no structure. Okay, so now a halo is accreted, and now it's a subhalo. Now what's going to happen? Well, it's going to orbit around in this host halo. And when it's orbiting around in this host halo, it feels tidal forces. It feels a strong tidal force from this host halo. And that tidal force will cause stripping of matter from the outskirts of the halo. We'll just strip it off. Okay? And if you want to predict now what is the mass function of halos at any given time, not the ones at accretion, but at any given time, you need to include a model for the stripping. Okay? So our model is excessively simple, okay? But it allows us to fit the data and it gives insight. The idea is the following. What matters for stripping is the tidal radius. You can compute at any moment in time, you can compute the radius, the tidal radius, and that's the radius outside of this radius. These particles here are basically no longer bound to him, but are bound to the host halo. In other words, they feel an acceleration due to the host halo that's larger than the acceleration they feel from the subhalo. So they will be stripped off. Okay? That's what's called the tidal radius. And the idea now is that once I'm here, a subhalo moving in, the tidal radius shrinks because my tidal force gets stronger inside the center. So the tidal radius is going to be the smallest at the pericentric passage of the subhalo, when it's closest to the center. And here comes a model for the stripping. It says, well, I'm going to assume that in an orbit average sense, the amount of mass that the subhalo loses is just the mass outside the tidal radius at pericenter. So just strip off that mass and assume that that mass is lost per radial orbit when it moves from pericenter to pericenter, or apocenter to apocenter. That's a model. Ridiculously simple. I can now go and do many realizations for that. I'm going to say, okay, let me draw halo concentrations. I know what the distribution of halo concentrations is. I know what the energy and angular momentum are of subhalos when they fall in. You can measure that from the simulation. Okay? So I can draw random values for the orbital energy and angular momentum. Once I know those, I can compute the pericenter. Okay? And once I know the structure of the halo and I know the pericenter, I can compute the tidal radius. And then from this equation, I can compute the mass loss rate. And that is what is plotted here. This is the average mass loss, or the mass loss rate for an individual realization as a function of the average mass of the subhalo. Each gray dot here is one realization. There's about 100,000 realizations in here. And they follow a very simple, beautiful power law with very little scatter. The scatter basically is just scatter coming from the scatter in the orbits, but it's not that dramatic. Okay? It actually turns out to be very well fit by a log normal distribution with a scatter of about 0.17 DAX. So that's not that bad. This functional form is very well fitted by a power law. Okay? The power law that says the mass loss rate is the mass divided by the dynamical time. This kind of makes sense. It's the time scale in which the thing is moving around.
Sorry, what's little m and big M?
This is the subhalo mass, this is the host halo mass.
It is, okay, that's fine. Okay.
So if this would not be here, this would be just exponential mass loss. Right? M dot is M over tau. That would be exponential mass loss. Turns out that the slope is slightly different from that, and we need to modify it with this thing here, but it's only a small correction. Zeta is only at 0.04, 0.07. Okay? So what we did in the end is we have an absolute normalization here, okay, which we get from this toy model, but we needed to tune it a little bit. And we tuned the zeta a little bit, but we only need to tune it a little bit, and we tune it so that we reproduce the simulation results for one particular mass scale.
So when you compute the pericenter, did you account for the dynamic friction?
No.
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 So basically, dynamic friction
So-
in this amplitude.
Excellent. Very good. So the physical interpretation of the fact that it's not perfectly power law is the fact that there is dynamical friction. Our toy model also gives a little slope of 0.04, and that comes from that concentration mass relation. Therefore, there's also no, that already gives you a little hint. But then if we fit it to the simulation results, we find 0.07, and we think this is due to dynamical friction. It's a really mild effect. Okay. Anyway, we have a model, we have a,
I
Yeah,
have a
sorry.
question about the energies and angular momentum of
Mhm.
the orbits. Are you, are those physically motivated in some way? How are you drawing the energy?
so they're basically derived from the simulation.
Okay.
In the simulation, you look at what are the properties, and that's basically what we draw from. So it turns out, and this was the hardest part, that what we initially ignored, it turns out that these subhalos not just lose mass, and just keep losing mass. It also, if you look at the simulations, what happens is these subhalos are moving around, they lose mass, and suddenly, boop, they're gone. They get disrupted. No particles remain that are bound to each other. The subhalos completely disrupt. And tomorrow I'll talk about why that is or why that might not be. But what we in the end struggled with is how we're going to reparameterize that, because we couldn't come up with a physical model to describe it. In fact, I still can't come up with a physical model to describe it. I suspect that it's largely numerical. but initially we were set to try and reproduce the numerical simulations. So what we did in the end is we just looked up some properties of the subhalos at the moment of disruption in the simulation. And what we looked up was basically this value of alpha, which is defined according to the following. So the mass of the subhalo at the moment of disruption, we write as a mass of the subhalo at accretion inside alpha times its scale radius. Okay, so it's a way of parameterizing this that people have done in the past. In fact, there's 3 previous models that use this kind of description to model disruption. And you see that all 3 people use very different values for alpha. If we measure this alpha in the simulations, we see that it's a very broad distribution. It cannot be modeled as a single value, what previous people have done. So we just fit a log normal to this, and that's what we use. So we're completely guided here by the simulation. Okay, but it has no free parameters. So we put that in, and now we're basically done. We have a model, we have a merger tree. Whenever something accretes onto the halo, we start applying the mass loss model. Okay, between any 2 time steps in our merger tree, each subhalo's mass is diminished by this amount. Okay? And once its mass is stripped down to this mass given by this equation, where alpha is a random value drawn from that log normal, I disrupt the subhalo. Okay? It's a very simple model. I can construct many, many realizations in just no time, and I can see how well does it do. Well, here is putting the model to the test. So this is my subhalo mass function. The number of subhalos is a function of the mass of the subhalo normalized by that of the host halo. The what is it, pink, for some reason, pink circles are the results from the simulation. This is for a host halo in this mass range, 10 to the 14 to 3 times 10 to the 14 solar masses, pretty massive halos. And the solid line is our model. Okay, so admittedly this is not a surprise that it fits because we have tuned it a little bit. Okay, but we fit it for this mass range, and we tune it for this mass range, and no longer tune in. Okay, the blue line for comparison is this unevolved subhalo mass function, this universal thing. So the difference between the blue line and this red stuff here, that is all due to mass stripping and disruption. Okay, so you see that there's a huge difference. Mass stripping and disruption are very efficient. The open circles here are what are the masses of the subhalos that survive to the present day, what were those masses at accretion. So it's like the unevolved subhalo mass function, but only for the subhalos that have survived. And that is given by these circles, and we see our model also can fit that nicely. And so the difference between that curve and the blue one, that's entirely due to disruption. So you see that disruption is extremely important. The vast majority of subhalos that have been accreted over the life of a halo are gone. They have been disrupted. The difference between these two, that's due to stripping. Okay. Now we can do the same thing with Vmax. Okay. For those of you who are interested, people are using Vmax a lot for abundance matching and that sort of stuff. So our model can predict that. We can test whether the model gets the ratio between the mass and the mass of accretion of subhalos correct, and it all works out. We've tested many more statistics, and it really, this model reproduces the simulation results very nicely. Partially because I tuned it to, and partially because the model that I use for disruption is taken from the simulation. But the nice thing is that now I have a model and I now can explore how it changes if I change cosmology, if I change my halo mass, okay? And that's what we're doing. I just wanted to show you again that survivability of the substructure. This is our model prediction now. Again, this is tuned to simulations. If you look at the black line, there's a fraction of subhalos that survive as a function of their accretion rate. Okay? Redshift accretion of 1 is here at 0.3, and you see that only about 35% of the subhalos that were accreted at redshift 1 have survived to the present day. 65% of those subhalos are gone, are disrupted. And if they have galaxies in them, probably the galaxies would also have been disrupted, although that's highly questionable. So disruption is very important. The question is, what is the cause of this disruption in the simulations? Is it physical or numerical? If you're interested in that question, I can advocate this seminar tomorrow. I can also tell you that I don't know the answer yet. So, now we can use the model to make some predictions. And one thing that I'm predicting is, for example, how does this evolved subhalo mass function change this function of halo mass, of the host halo? And that's what is shown here. So these are all different subhalo mass functions. Again, averages over many realizations. And going from blue for the most massive halos to red for the low mass halos. You see a dependence in the normalization. You basically see that the model predicts more massive halos have more substructure. Well, we immediately can understand this now. This makes sense. Remember, every subhalo builds up from the same building blocks, but the more massive halo builds up later. So their subhalos were accreted later, and they have been subjected to stripping and disruption for a shorter period of time. That's why the remaining mass function is higher. Okay? So it all makes sense. Now, is this consistent with the simulation results? Of course it is, otherwise I wouldn't be here. So here are the results from 2 simulations. This is this Bosch simulation again. You're going to see this rank ordering of the colors very nicely reproduced. Again, dotted lines are where the simulation runs out of juice. Okay? And at the massive end it's just noisy because you only have 1 or 2 of these subhalos on average. But the other thing to notice is that I'm comparing here Bosch to a multi-dark. Multi-dark is a bigger box simulation, and that's better suited to look at more massive halos because I have more of them, so my averages are better. So that's why here I go to very massive halos, and this one is more suited for low mass halos. And now look at the other thing, BDM and Rockstar. This is different subhalo finders run over the simulation. So it's the same simulation, here multi-dark and multi-dark, but here it's analyzed by Rockstar, this phase space finder for finding halos and subhalos. And here it's analyzed by BDM, it stands for Bound Density Maximum, Anatoly Klipin's subhalo finder. And if you look carefully, you can see huge differences. If you actually read off this difference, in the y direction, this is an order of magnitude different in the number of subhalos. This is the same simulation. It's just analyzed by different people. Okay? So people can say, why would you want to use analytical models if you can use simulations? Because simulations don't agree with each other. Okay? That's the reason. And this may give us some analytically motivated suggestion of which one of these 2 is better. Okay? You can read off for yourself which one that is. Now,
isn't it a better match just because you use rock?
yes, you're right. So in an absolute sense, I can't say anything.
So I mean, but does your conclusion that your physical conclusion you think holds still? That the bigger because they flipped the order of the rank order of them was different in 2 different panels, right? The blue ones are on the bottom in the left panel.
Oh, here. Yeah, this is just an artifact. And in BDM, there is a little sentence in the paper that describes that they're doing something. They have a problem when two or three subhalos, massive subhalos, are in the same host halo, and then they throw away a few. So they say that.
Okay.
So there's one sentence that says that they're doing something nasty when there's massive subhalos, and it only is a problem at the massive end. But the massive end is when you're interested in counting how many LMC and SMCs were predicted in Milky Way. That's what matters. But yeah, good eyes. So let me skip this because I want to go on to the rest. Basically, I've basically painted a picture of why subhalo mass functions are higher for massive halos and low mass halos. It all has its origin in this unevolved subhalo mass function, and earlier assembly means more stripping and therefore less surviving substructure. Okay? And it turns out that you can then use a model to make a prediction for how this changes with cosmology, and it all fits into one same thing. So again, you can write down one functional form that describes the subhalo mass function for any halo mass in any cosmology. Okay? This is something that I found very disturbing, and that Zheng Jing should find very disturbing. Halo occupation modeling. Halo occupation modeling is a business where what we try to constrain is Pn given m. This says, given a halo of mass m, how many galaxies does that halo have of a certain property? So galaxies that are brighter than some magnitude. Okay, that's what people try to measure. And all these models assume that this is a proper functional form to describe what is going on. In reality, the number of n also depends on the formation redshift of the halo. Given what I've just painted you, a halo that forms earlier, and if I look at halos of a given mass, they don't all form at the same time. Some halos of a given mass form a little bit earlier, and some halos form a little bit later. Those that form a little bit earlier, on average, should have more of their substructure erased. They will have fewer subhalos. They will have, therefore, fewer satellite galaxies. So a natural prediction of the CDM paradigm actually is that P of n should be a function of m and formation redshift. In fact, that's exactly what our model predicts. So this is now the number of subhalos as a function of host halo mass. The black line is for all of them. This looks exactly like one of these HOD models that Zheng always constructs. But now we have split the halos in the early formers and the late formers, and it clearly separates out. And this is not a small effect. If you translate this into a correlation function, this is very important. So not only do the number of subhalos depend on the formation time, this clustering strength of halos also depends on the formation time of the halo. As it turns out, halos that form earlier are more strongly clustered than halos that form later. This is called halo assembly bias. And if you take those two things in combination, it basically means that halos with few satellite galaxies will be more strongly clustered than halos with the same mass with a lot of substructure. And that is something that no one has taken into account, and I'm guilty as charged too. I've written a whole bunch of papers ignoring this, kind of not knowing about it, but in retrospect I should have known about it. And this is something that potentially can lead to significant systematic errors in all this HOE business.
But this the first factor, like the observation that this number also depends on the redshift. That this doesn't matter. This assembly bias is the most important effect. Because the first factor, supposed to be captured by this probability distribution. You have dependent
If
on
you integrate over it, yeah.
yes.
But it's a combination of the two that is damaging. I agree.
Yeah.
This by itself is not an issue, but it's a combination of the two
Yes.
that's damaging. Yeah, I agree. Anyway, the last 3-4 minutes, let me very quickly go through too big to fail. Too big to fail is a problem that was pointed out in a paper by Mike Bohr and Colloquium. He basically pointed out that the Milky Way has 0 satellite galaxies with a maximum circular velocity between 25 and 60 kilometers per second. Whereas numerical simulations predict 5 to 10 of such subhalos, and if they exist, those subhalos will be way too massive to have failed to form a galaxy. One might argue that really low mass halos with a circular velocity curve below 25 kilometers per second, they cannot hang on to their gas. You can imagine ways in which galaxy formation doesn't work there. But in a halo from 25 to 60 kilometers per second, that's a deep potential well, a galaxy should have formed. So they pointed out these subhalos, if they exist, are too big to fail making a galaxy. And it's sort of illustrated here. This is the circular velocity curve as function of radius. Each curve here is a subhalo in a numerical simulation, okay, of a Milky Way sized halo. This is the Aquarius E simulation. This is the mass of the host halo. So these are all the subhalos they find. And these are measurements from dwarf galaxies in the Milky Way, where people measured at a certain radius, they measured in an enclosed mass using some kinematical tracers. Okay? And all these dashed curves are basically subhalos that are consistent with hosting one of these satellite galaxies. But there's a whole bunch of them here that are not consistent with any of these dwarf galaxies, and their argument is they should also host that galaxy, and why haven't we seen that galaxy? Why haven't we seen those? And this has become really an annoying problem, and many people have been written on it. Of course, when you post a problem, then theorists go crazy, and people say, oh, dark matter is not cold, it must be warm, or it must be self-interacting. Other people will go to more mundane solutions, like maybe galaxy formation can change the central density of a dark matter profile and make the rotation curves lower. That's certainly a viable solution. But maybe it's even more boring than that. That statement about too big to fail was based on 5 or 6 simulations of a Milky Way sized halos. 5 or 6 independent realizations. Using our model, we can predict what is the halo-to-halo variance. Okay? And that's what is shown here. Just look at this. This is for a halo of 10 to the 3 times 10 to the 30 solar masses. Each pink curve is from a simulation, actually. This is from the Bosch simulation. The number of subhalos with a Vmax larger than this value. Okay, so this is the cumulative subhalo velocity function, if you want. And you see that these are all the same mass, but there's a huge halo-to-halo variance. Okay? And in gray underneath it are our model predictions. Okay? And you see some slices through it here. And basically, the point that we want to make here is our model not only predicts the average correctly, it also predicts the variance, the halo-to-halo variance correctly. And therefore, we can now make our model, and rather than make 6 realizations of a Milky Way, we can make 10,000 realizations and actually do proper statistics. That's what we've done. Since I'm running out of time, here is the sort of the main plot. This is the number of subhalos with a Vmax larger than this value. Well, there's one in the Milky Way that has a Vmax of about 90 kilometers per second. That's the LMC. The next one is the SMC at about 60. Then there's this gap towards 25 kilometers per second in Sagittarius, and then there's a whole bunch of dwarf galaxies. And people have argued this gap, that's a problem. Okay? And we can't reproduce that. Well, we made 10,000 Milky Ways of 10 to the 12 solar masses, and we found 6 out of 10,000 that reproduce that gap. They reproduce a gap, they have a problem here. We'll come back to that later on. Okay? But they reproduce a gap. So we can reproduce a gap. Here's one of these realizations, the LMC, SMC, and then a whole bunch of them, and they're consistent with the data. So, first of all, it can happen, but 6 out of 10,000 is kind of on the problematic side. Okay? That's only 0.3% of the Milky Way sized halos do that. Of course, this is statistics with 1, which is kind of stupid. And now you can argue, does this rule out lambda CDM or not? The main point is, the entire question that people are asking here is wrong. Particle physicists know this is a look elsewhere effect. What people have asked is, what is the probability that I have a gap from 25 to 60 kilometers per second between my second and third most massive subhalo? That's like a very specific question. If you ask the question, what is the probability that the first satellite has this Vmax, the second one has this Vmax, the third one has this Vmax, then the answer is 0. Okay? But there's nothing wrong with this curve. What if the gap appeared between the third and the fourth most massive subhalo? And what if the gap was between 75 and 35 kilometers per second? That was also a gap. So you can't ask this very specific question. It's a stupid question to ask. Okay? So we try to do this without this problem, comparing the full distribution of the Vmaxes predicted by our model to the Milky Way, and coming up with a test. It's sort of similar to the Kolmogorov-Smirnov test. For those of you who are familiar with it, you compare cumulative distributions. The Kolmogorov-Smirnov test looks at what is the maximum distance between the two cumulative curves. That's very good for measuring whether two distributions have the same mean, because if you have a slight offset, then that translates into that. But if the distributions have the same mean but different wings, the Kolmogorov-Smirnov test has no sensitivity. So we devise it, and basically what we measure is not the maximum distance between the two curves, but the entire area between the two curves. You can turn that into a simple statistic, straightforward, and with 10,000 realizations, it's a piece of cake. And we can ask the same question, what is the probability that you get something like the Milky Way from all the realizations of 10,000 Milky Way halos? We can do that 10,000 realizations of 10 to the 11 solar masses, 10 to the 5 solar masses, 10 to the 12 solar masses. So we have mass here. And if we try to see what is the probability of reproducing the 5 most massive systems in the Milky Way, those are the ones for which we have really good data, we get the red curve. And if we believe that it's about 10 to the 12 solar masses, then the probability is about 10%. And 10% I'm not going to be awake about, and 10% I'm not even going to write a paper about, 10% is boring. In fact, that 10% has an uncertainty, and that's because each individual Vmax measurement of each individual satellite has an error in it. Okay, you can propagate that error, and that gives you an uncertainty on that probability, and that's given by this error bar. So if you take that into account, there really isn't a problem. Okay? Now, what if you take all 20 galaxies, subhalos, into account? Well, now we have a problem. Even unless you are willing to accept that the Milky Way has a mass of 3 times 10 to the 11, which basically no one wants to accept. Okay? This is sort of the range that people are bitching about. You know? But there, at 10 to the 12, that's really ruled out. Okay? And the reason is, and this 20 is not a good number because people keep discovering new satellite galaxies all the time. This is assuming that we're not going to discover any new satellite galaxy with a Vmax larger than 10 kilometers per second. If all the new dwarf galaxies we keep discovering on a daily basis have a Vmax less than 10 kilometers per second, and 10 years from now we still have no new galaxies with above 10 kilometers, then this is what it looks like. Then we have a problem unless you can come up with a solution involving galaxy formation. N is 9, the intermediate number. If you ask the experts, down to what limit are we complete today? Okay, which can we trust? They say, well, the first 9 we're complete. We're not going to find anything with a Vmax larger than any of those. That's the black line. Now you sit sort of, again, within the error bar still. I'm not too worried about it. But it's clear that the too big to fail problem was highly exaggerated, largely due to poor statistics and mainly applying a poor statistic to the data. All right, conclusions. CDM halos have a universal density profile. We've known that for a long time. Shown you that they also have a universal mass accretion history. That's why they have a universal density profile. And they also have a universal subhalo mass function. And again, that comes from the fact that all of this is universal. All of this scales with halo formation time. That's the one parameter that basically describes what the structure of a halo looks like and how it forms. And the assembly of dark matter halos, therefore, I would say is a solved problem. It simply captures all relevant scale-free physics, operating on scale-free initial conditions. and I'll leave this up for you to read. And tomorrow I'm going to talk about evolution of subhalos, and while I take questions, I can run this movie that sort of shows what I'm going to talk about tomorrow. So, thank you.
Questions from the audience?
You mentioned lensing.
Mhm.
I can understand baryonic effects and probably also dark matter effects. What about subhalo effects on lensing? How do you know that?
We have a potential well. The light goes through it, gets reflected, right? So if I draw that, okay, my light goes through and does this. Now I put a subhalo here. Now my light gets reflected and does something like that. So it creates wobbles. And I suppose the other light curve made me here. I have a multiple lens system. Okay, so I see the same system here, and I see it there. I see it here and there. This line of sight went through a substructure, and this one did not. That causes a change in the time delays. So then I see changes. If this one fluctuates, I see it first here and then there. And that's how you can sort of have a sensitivity to that substructure.
Other questions?
This is actually related to your introduction at the beginning. And how confident are we that the first 10 to the minus 31 seconds actually lasted 10 to the minus 31 seconds and not anything else? I mean, I hear this all the time. I'm always fascinated by people
I
who
did a
can
talk this
make a
morning,
statement like
and I said it
that.
was 10 to the minus 34 seconds.
Or 34, I mean.
No, he said 10 to the minus 31.
It started at 10 to the minus 31, and it lasted, no, 10 to the minus 34, and it lasted for about 10 to the minus 31. So from 10 to the minus 34 to 10 to the minus 31 seconds.
That's 10 to the
But-
minus 36, 10 to the minus 34.
So the answer is we are not very certain. The only thing that we know, we know that it has to last a certain amount of time. It has to last 60 e-fold times, 50 to 60 e-fold times, and that's basically the constraint for it to stretch out large enough to explain a few daunting issues. For example, if we look at a cosmic microwave background there, and there it's the same temperature. Yet, without inflation, they cannot have been in causal contact. How can that patch of the universe know about that patch of the universe? But if we have stretched it for long enough, then they actually come out of each other's horizon, and that puts a constraint. We need about 50 to 60 e-fold times. I have asked the same question to other people, why can't it be 150 e-fold times? What's wrong with that? And I still do not know the answer. So if anyone understands why there's an upper bound, where that comes from, I would love to hear
I
that.
don't think there's an upper bound.
Yeah,
That's what I said. It should be, the number of
But-
e-foldings can be,
yeah, I have the same impression.
It
So
ties in some way to the scalar tilt in the power spectrum and to the scalar to tensor ratio. I can't remember exactly how that works, but I think that might put some constraint on it. And the running of the
but that has more to do with the running. Instead
the
of
running, I think, if you
But
have
then-
an infinite number of e-foldings, the running has to be 0, I think.
So maybe for the single field inflation model and a single power law slope, you can actually translate it into it. It can't be much more than that. But there's so much freedom in inflation space that you can do anything you want.
Yeah, remember the constraint from CMB, you see the tensor scalar ratio, and they have this contrast.
Right.
This inflation model with different default.
I mean, does it even make sense to define? I mean, our time is defined by essentially the fine structure of a hydrogen atom and how it ticks nowadays. And at the time when you don't even have, you know, when protons or even when protons have not even condensed, what's the meaning of time then? You know, when, you know.
If I understood the meaning of time,
Okay.
I'm looking at Oslo right now.
There's no clock. There's no clock that ticks, basically. Nowadays we have everything that moves around is time passing by, and these are our clocks that scale our time.
You're asking very deep questions to which I unfortunately don't have the answer.
Well,
I think you can probably make a ladder of shorter, different times.
Right.
that-
So it's just different clocks then.
Yeah.
we try to make measurements of the fine structure constant but you can't go all the way back that far.
Mm.
But we try to measure cosmic evolution, the fine structure constant, you don't see anything. To over 10 billion years. John, and then I'll come
Very,
back to
very,
this.
I hope it's a simpler question. You make an issue of scale invariance or something like that, like gravity doesn't have scale to it.
Mhm.
What does? I mean, what?
The weak force. The weak force acts out of a certain scale.
It has a length. Okay.
Yeah, it's typical length scale associated with it. So
Electromagnetism.
electromagnetism, to some extent it does have, because beyond a certain scale you get shielding effects, right? And basically electromagnetism, that's why gravity, although the EM force is much stronger, gravity dominates on large scale because it's shielded, because you have as many negative and positive. So there's a characteristic scale that comes in there that has to do with how the positive and negative charges are separated out. In gravity you don't even have that, right? You can build a Faraday cage and shield yourself from the EM. You can't do the same thing in gravity. So that's why gravity really is utterly skill-free.
That reminds me of a question of a friend of mine. His son asked him, the glass fell off the kitchen table and broke. And he said, well, that's because of gravity. So the kid wants to know, how did the gravity get into the kitchen?
So maybe we can take one more question, and then people can ask questions afterwards.
So I just had a question about the universal time that you defined. And it had this complicated expression coming from the press chapter. Is there a physical way to just visualize what this time actually means?
Yes, it has to do with perturbation, with basically when the perturbations turn around. Okay? And the perturbation turns around when its overdensity becomes of order unity. And when you start out with perturbations with no scale in it, then in density, then the perturbations on small scales are larger than perturbations on small scales. So the scale freeness is in the potential, but in density, small fluctuations have larger perturbations than more small ones. Since the small fluctuations on small scales have larger fluctuations, they will collapse first, and the big ones will collapse later. And that's sort of that's sort of where it ultimately comes from. That's why you have a hierarchical structure formation. The way to think about it, another way, a very simple to think about it, is you have big fluctuations, and on top of that you have small fluctuations. On top of that you have small fluctuations. Which ones are the ones that are going to collapse first? Well, there's a cutoff here. These ones are going to collapse first. So those are small ones. Okay? And then this one, and ultimately this one. And therefore the small things collapse first, the big things collapse first. And that time derivative basically has that information in there. Basically tells you when are you going to turn around and collapse.
Very good questions. Let's thank the speaker one more time. And again, as a reminder, Frank will be presenting tomorrow's HEAP seminar at 11 o'clock over my SCC.
The answer is that gravity was there before the
Thank you very much. So, do you want to go to the guest house? Do you want to hang out here? Whatever you're comfortable with. I mean, neither of us have a car. So I think we'd be left to walk in the guest house, but it's pretty nice out. Or you could stay here, and Jenga's staying here, and I'll pick Jenga to 7:15.
Yeah, maybe I'll go to the guest house. Chill out a bit.
Yeah, I think that would be.
So-
That's what I would. That's what I would think.
And then you guys pick me up there?
I'll pick you up at about 7:15 if you guys have.
7:15? Yeah, inside then.
Okay. So I gotta run home, but I'll see you in a couple hours.
So it's okay if I can walk over there? You don't want to walk over there? Yeah.
It's pretty nice out.
It's gorgeous.
Okay, I'll see you in 2 hours.
Alright.
I'll just take